Right now, as you hear this sentence, your heart is beating. It beat while you slept last night. It beat during every exam you've ever taken, every argument you've ever had, every moment of boredom, panic, love, and grief you've ever experienced. It has not stopped since roughly 3 weeks after you were conceived. By the time you finish this video, it will have beaten another 1,000 times. Over the course of an average human life, it will beat roughly 2.5 billion times. No rest days, no maintenance windows, no off switch. Every other muscle in your body fatigues. Your legs give out after a marathon. Your arms fail after minutes of holding weight above your head. Your heart contracts with the same force at the same reliability for 80 years straight. Why? Why doesn't it get tired? In the next 13 minutes, we'll answer that question. And what we find will take us to places most people never expect. The heart is not merely a pump. The heart is not merely a pump. It is an electrically independent organ that generates its own rhythm without any signal from the brain. Its muscle cells are architecturally unique, built to resist fatigue at the molecular level in ways no other tissue in the body can match. When it fails, you have roughly 4 minutes before the brain begins to die, and the device that has saved more lives than any other in history. Most people learn in school that the heart is a pump, 4 chambers, valves, blood in, blood out. This is true as far as it goes. But it misses the most remarkable thing about the heart, the thing that separates it from every pump humans have ever engineered. A mechanical pump needs an external power source. It needs a controller telling it when to cycle. It needs maintenance, replacement parts, scheduled downtime. Your heart needs none of these things. It generates its own electrical signal. It powers its own contractions. It maintains its own rhythm. And it does this without any instruction from the brain. If you severed every nerve connecting the heart to the central nervous system, it would keep beating. This is not a metaphor. It is a verifiable, observable fact. The heart is, in the most literal sense, autonomous. The source of the heart's independence is a small cluster of cells in the upper wall of the right atrium called the sinoatrial node, the SA node. These cells are unlike any other cells in the body. They are autorhythmic. They spontaneously depolarize, generate their own electrical impulse, roughly once every 0.8 seconds without any external trigger. No nerve signal, no hormonal command. The impulse originates within the cells themselves, driven by the slow leak of sodium and calcium ions across their membranes. When the SA node fires, the electrical impulse spreads across both atria, causing them to contract. The signal then reaches the atrioventricular node, the AV node, which delays it for a fraction of a second, allowing the atria to finish emptying before the ventricles contract. The impulse then races down the bundle of His, splits into the left and right bundle branches, and fans out through the Purkinje fibers, a network of specialized conduction cells that deliver the signal to every ventricular muscle fiber almost simultaneously. The entire sequence, from SA node firing to full ventricular contraction, takes less than a quarter of a second. And here is something that makes the heart's electrical design even more remarkable. It has built-in redundancy. If the SA node fails, the AV node can take over as pacemaker, at a slower rate, roughly 40 to 60 beats per minute, but sufficient to sustain life. If the AV node also fails, the Purkinje fibers themselves can generate a basic rhythm, roughly 20 to 40 beats per minute. Slower, less efficient, but still capable of keeping blood moving. The heart has 3 independent backup pacemakers nested inside each other. No human engineer has ever designed a system with this level of self-contained redundancy. The heart was solving the engineering problem of autonomous reliability billions of years before humans invented the concept. So if the heart doesn't need the brain to beat, what does the brain do? It modulates. The autonomic nervous system adjusts the heart rate based on what the body needs. Exercise, fear, excitement. The sympathetic system accelerates the SA node. Rest, digestion, sleep. The parasympathetic system, through the vagus nerve, slows it down. But neither system initiates the heartbeat. They adjust a rhythm that already exists. The brain is the thermostat, not the furnace. Remove the thermostat, and the furnace keeps burning. This is exactly what happens when a heart is transplanted. Every nerve connection is severed. The transplanted heart beats at a steady resting rate, typically around 100 beats per minute, faster than normal, because the vagus nerve that usually slows it down is gone. But it beats perfectly well for years. Now the harder question. Electrical independence explains the rhythm, but it doesn't explain why the muscle itself never tires. Skeletal muscle fatigues after sustained contraction because it runs out of energy faster than it can replenish it. Cardiac muscle has solved this at the cellular level in 3 ways no other tissue replicates. First, mitochondrial density. Cardiac cells contain roughly twice as many mitochondria as skeletal muscle cells. Mitochondria produce ATP, the molecular fuel for contraction. In cardiac cells, they occupy roughly 35% of the cell's total volume. No other cell type comes close. Second, continuous fuel supply. The heart receives its own dedicated blood supply through the coronary arteries and extracts oxygen at roughly 75% efficiency, compared to about 25% for resting skeletal muscle. The heart runs at near maximum oxygen extraction all the time. It doesn't have a higher gear. Third, and this is the most elegant feature, cardiac muscle has a built-in mandatory rest period. It is called the absolute refractory period. After a cardiac muscle cell fires, it becomes electrically unresponsive for roughly 200 to 300 milliseconds. During this window, no stimulus, no matter how strong, can make it contract again. This is not a limitation. It is a design feature. The refractory period guarantees that the heart cannot sustain a continuous contraction, a tetanus, the way skeletal muscle can. It forces the heart to relax between beats. Every beat includes built-in recovery time. This means the heart, by its very nature, cannot overwork itself into a cramp. It is the only muscle in the body that is architecturally incapable of sustained contraction. It must rest between beats. It was designed to be inexhaustible. And yet, for all of its redundancy and resilience, the heart can fail. When it does, the consequences are immediate and catastrophic. In sudden cardiac arrest, the heart's electrical system malfunctions. Instead of the orderly SA node to AV node sequence, the ventricles begin firing chaotically, a condition called ventricular fibrillation. The heart quivers instead of pumping. Blood flow to the brain drops to 0. Within 10 seconds, the person loses consciousness. Within 60 seconds, breathing stops. Within 4 minutes, 240 seconds, brain cells begin to die irreversibly. After 10 minutes without circulation, survival with intact neurological function is rare. The heart, which ran flawlessly for decades, has a failure mode so catastrophic that it kills faster than almost any other medical emergency. The margin between life and death is measured in minutes. This is why the defibrillator exists. Its function is widely misunderstood. It does not restart a stopped heart. It stops a chaotic one. The electrical shock delivered by a defibrillator depolarizes every cardiac cell simultaneously. A hard reset. For a fraction of a second, the entire heart goes electrically silent. And then, if the SA node is still functional, it fires. The heart's built-in pacemaker reasserts itself. The rhythm returns. The defibrillator doesn't create a heartbeat. It clears the chaos so the heart's own system can take over again. It is, in the deepest sense, a tool designed to get out of the heart's way. In 1956, an electrical engineer named Wilson Greatbatch was working at the University of Buffalo, building a small oscillator circuit intended to record heart sounds. The circuit required a specific resistor, a 10,000 ohm component. Greatbatch reached into his parts box and, without checking, pulled out the wrong one. He installed a 1 mega ohm resistor. When he switched the circuit on, it didn't record heart sounds, it produced them. The circuit emitted a steady rhythmic electrical pulse, about 1.8 volts once per second. Greatbatch stared at it. The pulse looked exactly like a heartbeat. He immediately understood what he had built. Not a recorder, a generator, an artificial pacemaker small enough to implant inside the human body. Within 2 years, Greatbatch had built a prototype sealed in epoxy to protect it from body fluids. In 1960, the first fully implantable pacemaker was placed in a human patient. In 1960, the first fully implantable pacemaker was placed in a human patient by surgeon William Chardak at the Veterans Administration Hospital in Buffalo. By the 1970s, lithium batteries replaced earlier zinc cells. Leads became thinner. Programmable circuits allowed cardiologists to adjust pacing rates without surgery. Today, over 1 million pacemakers are implanted worldwide every year. More than 3 million people are alive right now with a pacemaker in their chest. A tiny circuit that does what the SA node can no longer do, delivering an electrical pulse once every 0.8 seconds, keeping the rhythm that keeps them alive. All because an engineer reached for the wrong resistor. The pacemaker was only the beginning. When the problem isn't a missing rhythm but a chaotic one, the implantable cardioverter defibrillator, the ICD, monitors the heart continuously. The device that paramedics use externally, the ICD, carries inside the body permanently, always ready. When the problem is mechanical, when the muscle itself is failing, medicine has learned to replace the organ entirely. Since Christian Barnard performed the first human heart transplant in Cape Town in 1967, the procedure has become routine. Over 5,000 heart transplants are performed worldwide each year. Transplanted hearts, as we discussed, beat without nerve connections. Further proof that the heart's independence is not a theory, but an observable feature of the organ itself. And now, the frontier. Researchers are developing bioengineered heart tissue, lab-grown cardiac muscle cells that beat spontaneously, just like native tissue. Stem cell therapies aim to regenerate damaged heart muscle after heart attacks, replacing scar tissue with functional beating cells. And fully artificial hearts are in advanced clinical trials. Each of these technologies builds on the same insight Greatbatch stumbled into in 1956. The heart's rhythm is not a mystery to be replicated from scratch. It is a property of cardiac tissue itself. Give the cells the right environment, and they will beat. The rhythm is in their nature. Here is what the heart teaches us about the design of living systems. The most reliable machine in the human body is not controlled by the brain. It is not maintained by conscious effort. It does not require rest in the way we understand rest. It includes its own power generation, its own timing mechanism, 3 layers of backup, a mandatory recovery period built into every cycle, and enough fuel efficiency to run at maximum output for a century. No engineering team in history has built anything that comes close. The most advanced artificial hearts last 5 to 10 years. The biological heart lasts 80, performing more total work than any machine humans have ever constructed. Right now, as this sentence ends, your heart is beating. It beat again in 0.8 seconds, and again after that. It has been doing this since before you were born, and somewhere in your chest, a cluster of cells the size of a pencil eraser is generating the electrical impulse that makes all of this possible. Without instruction, without rest, without help. That is what the heart actually is. Not a pump, a self-sustaining, electrically independent, architecturally inexhaustible system that decided roughly 3 weeks after you were conceived to start and never stopped.